Being recorded. Yes, we'll prove this. Do you want me to say your title or not? I don't say the title because people like to give their own titles.
Yeah, you don't have to.
Wanna...
I think I have it. If I, we'll see what comes out of it.
How do I pronounce your name? Catherine Whitaker.
You can call me Kate.
Kate Whitaker.
Yeah, perfect.
Mind if I take a look?
Other thing, like I could finish my pretty party skill. Yeah, we're so bad.
I think we're just.
Yeah. Wait one more minute.
Yeah, because there was.
No, I should just. All right. What's gonna go? Are you doing astrology? Welcome back from coffee, everyone. Thank you. So we have the pleasure of Kate Whitaker for starting us off in this session.
Thank you. So hi, my name is Kate Whitaker. I am an associate professor at UMass Amherst, and I'm really excited today to talk to you about what I feel is a new look towards the next era, if you will, of galaxy formation. And so in this talk, I wanted to focus on lessons learned and the discoveries that we've made in the last year since the JWST data first dropped. And you can see, for example, starting with this amazing phenomenal image of the SMAX cluster that was released a year ago yesterday to us. And so it's my hope to really build on the galaxies talks that we've had so far, hopefully, hopefully not be too redundant here, and talk about how we can use these new discoveries and what we've learned to shape future missions. And so a year ago yesterday, I was so excited to be watching the president's briefing from my own backyard. I was on Zoom with a couple of close colleagues as we were watching and cheering on folks that we knew that were in the room, but also having my family around me and having them pop over my shoulder and look at these images with me. And so it's really been quite a remarkable journey over the last year, and both in terms of, I feel like from the moment that Webb was launched on Christmas Day, I don't know about you guys, but I personally ruined my family's Christmas morning because I refused to leave the couch. I wanted to see everything. I was glued. My kids were more interested in opening presents. I don't regret one moment of that, but we still don't talk about that. In any case, it's really been a roller coaster of remarkable discoveries, which I'll talk about, and also remarkable challenges. And I think we've learned a lot already. So what did I do when I saw this image and they allowed us to download the high resolution version? I zoomed in, of course. This is not zooming in, but it is zooming in. PowerPoint, I tell you. So this is zooming in on one of those regions. And the level of detail that we could see with these new Webb images immediately blew my mind. In particular, one of the first galaxies that I noticed is right here, this one right here. What are those tiny dots? Are we seeing globular clusters in a distant lensed galaxy? Yes, my goodness. So this is one of the early papers on this particular object, led by Lamia Molla, and where she is modeling, and in this paper they're modeling the photometry and confirming that several of these compact point sources around this galaxy are consistent with globular cluster candidates, where they have formed remarkably early in the universe. So this particular galaxy is at a redshift of 1.4. At that point, the universe is about 4.6 billion years old. It's about the age of our solar system. We started our day with the solar system. So this galaxy is existing before anything, I guess, where we are today was existing. And in it already, you see these relics of really the oldest star formation in the universe, some of the first structures that formed very early and quenched very early. And so, honestly, it was just remarkable to see this level of detail. And I think for me, as a side note, I study quenching and I want to understand massive galaxy formation. So already seeing a new avenue of, my goodness, we can study globular clusters in distant galaxies and understand their stellar populations and understand quenching. And perhaps this feeds into how, if they migrate to the center, how we formed bulges of galaxies and piecing this story all together. Stay tuned. Lamia and her team were awarded Cycle 2 observations, spectroscopic follow-up, so we're going to be able to confirm if these are indeed globular clusters and learn more about their stellar populations. Now, if we zoom to another part of the image, which is on the HabWorlds sticker, I did not know that a priori. You see this really weird-looking, strong-lensed galaxy. Another really striking example. So what did this look like in earlier Hubble imaging? We could see it, for sure, but the level of detail that you're drawing out with this new facility and this new technology is astounding, right? I thank you for those wows. I appreciate it. Now, one of the first things we wanted to do, since Webb is opening up the red universe, is, okay, what do the red galaxies look like? And so we can zoom to another part of this image, and there were several early papers on the morphologies of red galaxies in these deep fields. This is one led by Fudamoto, and this was emphasized also yesterday in Rebecca's talk, the power of Spitzer. So it's not like we didn't know many of these red galaxies existed. We had Spitzer observations, and those Spitzer observations held their place in terms of both distant galaxies, but also constraining stellar masses of galaxies across cosmic time. Really critical for that. What did this galaxy look like before? Sorry, not before, in Spitzer imaging. Just really astounding. The whole new in terms of the resolution. Okay, here's one more example. We're not in the SMAX cluster in this next one. This is a cluster targeted by the PEARLS GTO program. And this one's another funny looking one. It's nicknamed El Anzuela, which stands for the, apologies for my lack of ability to pronounce that, stands for the fish hook. You can see for obvious reasons it looks like a fish hook. A remarkably red color, and in this study, they found something pretty striking where if you looked at the morphology from 1 micron out to 5 micron, pretty much looked the same size. The light had the same distribution. But if you combine the suite of imaging from NIRCam, it has a remarkable color variation. It looks like almost like fireworks, or I don't know, very pretty. And so in this study, led by Patrick Kamenetsky, he's a UMass PhD student. I should be able to say his last name. I'm sorry, Patrick. I always just call you Patrick. Fail. Hope he's not listening. Patrick did an excellent job here and in studying this in gross amount of detail. And so again, I'm showing you all strong lens. These are strong lens clusters. This is another gravitationally lensed galaxy. Where in this, we see a strong color gradient. And this is interpreted to be, because the size is the same, a strong gradient in dust. But also, if we look at the source reconstruction here, you can see added in as the ALMA contour, there's an offset between the ultraviolet optical light and where the dust is. And so this is quite common in distant dusty star-forming galaxies, where we see that the UV and the IR are not co-spatial, which would represent patchy dust, especially at higher redshift. I hope I've convinced you that with new technology, and in particular with the leap in terms of sensitivity and resolution, we're just seeing a whole new view of galaxies in the distant universe. And shown here is a very scientific plot showing the size of telescopes and the level of detail that we see. As telescopes get bigger, we have this improvement in sensitivity, we have this improvement in resolution, and we can just see a much higher level detail of the building blocks of galaxies. So going from global measurements to actually figuring out the building blocks of these galaxies. And so today, you can tell I've historically done more stuff with LUVOIR, so I'm going to keep on my die-hard LUVOIR. But really, in terms of HabWorlds, I'm using this as an umbrella term of a big telescope, a Keck in space. Something large, the bigger the better, in my opinion, though I understand limitations. And so this next plot was shown to you yesterday by Rebecca, and this is showing the sensitivity as a function of wavelength. And this is where we're at with Hubble. And those images I showed you here around the same wavelength, when we saw that fade between HST and JWST, is a little bit a combination of the longer wavelength lever arm that we have with Webb, but also this increased sensitivity from going by almost a factor of 3 increase in the mirror size. So this is sort of, I guess, where we're at in terms of sensitivity and resolution today. Where are we going in the future? So this is where ELTs, big ground-based, giant ground-based telescopes will place. And so what you'll see is we'll extend similar sensitivity in the optical, but really we've hit a plateau in sensitivity. And if you want to go deeper, we need to go to space and we need a big telescope. And so on here is shown the sensitivity of something like LUVOIR B, which I believe is close to the current thought process of HabWorlds, or LUVOIR A as shown. And so not only is it sensitivity, but it's also resolution and the level of detail that we're seeing. The bigger you go, the finer the detail you can see. And it's both of those things that are critical. And getting into this interesting regime here, not only probing, lower mass, fainter galaxies, higher redshift, but starting to get into very interesting parameter space where, for example, you might see the first POP3 candidate stars and other things where you need to break this threshold of getting down below 30 AV magnitude. And so here is showing you 2.8 hours, but I think the novelty of a plot like this is the relative scaling of how much time you invest. So sure, you could always try to convince some TAC that I want all the time, give it all to me, but it's the relative efficiency of these different telescopes. And so that should never limit, for any given sensitivity, how broad we think, of course. But it's really much more efficient and therefore can accomplish a wider range of science. So I'm going to focus on lessons learned from Hubble and Webb in this last year and talking about the red universe. So I wanted to start with this quote: "Discoveries are often made by not following instructions, by going off the main road, by trying the untried." And so the coolest thing often about deep surveys are those unknown unknowns, the things you don't quite know what to write into your survey. And this was absolutely the case when the first Webb data came down. So I want to tell you the story, at least one story of new discoveries made that actually I think were alluded to in an earlier question. So the data arrives, we see something new, we don't understand it, and that's where the fun begins. So this is a story of a candidate population of massive galaxies in the early universe. So this is now the SEERS data. The SEERS early release science data came down. It's immediately public. And so with a couple of colleagues, we downloaded this data. We were looking for those red galaxies. In particular, my colleague Erica Nelson came up with a sample and shared them right before sort of signing off to go to bed. Another colleague of mine, Rachel Bazanson, looked at it and said, "What the heck? That's a really red galaxy, and it says it's redshift 10. How on earth could you have a Lyman break and a Balmer break and be at redshift 10 when the universe is only 500 million years old?" That second Balmer break would be consistent with many low mass, older stars. You have to be very old and therefore very massive early on in the universe. What? So this sort of steamrolled, and Ivo Lebe led this work of then time zone win. He's in Australia, so we can all go to bed and can carry on the work of searching for more of these. And we found 6 candidates within SEERS. SEERS was at this point was a pretty small field of view for that first epoch of data. And you can see these candidate galaxies, and this is their composite SED. They're very red. You have these 2 breaks, and they're much redder than earlier HST and Spitzer known objects at these high redshifts. So what are they? And so we nicknamed them jokingly the universe breakers, because we thought we broke the universe. Why do I say that? Around the same time, there was also a paper a theory paper led by Mike Boylan-Kolchin, and this is showing a couple of the most extreme examples from the Labe et al. Paper, showing that you'd have to have an extremely high efficiency of forming stars in these galaxies very early on in these early dark matter halos for them to be so massive so early. And to the point where it's really challenging lambda CDM. Now, this is where the story turns. It's new discoveries. You're trying to understand things. Are there other interpretations? Yes, there are other interpretations. There's 2 sort of obvious things. One could be that we have emission line boosting, and it's much more extreme in the early universe than in nearby galaxies. And so if you have a ton of emission line boosting, we're overestimating the masses. They're not actually that massive. Another interpretation is, well, we got the redshift wrong. They're not actually at that high of a redshift. And this was a really common theme in this last year of data of both of those things in terms of degeneracies. Is it a redshift 16 galaxy? Is it a redshift 4 galaxy? And Rebecca talked about this yesterday a little bit. So one of the beautiful things about the SEERS program in particular is that they designed it to use a wide range of the instruments. And so they had follow-up near-spec spectroscopy, and at that point, they added some of the candidate universe breakers onto their slit to get follow-up spectroscopy. And so one thing I haven't yet pointed out is if you look at these, you'll see that they're all remarkably small and remarkably compact, very little. And so this one particular galaxy got near-spec spectroscopy, and a paper led by Dale Kozewski on the SEERS team came up with another alternative explanation of this is not a very massive high redshift galaxy. We got the redshift wrong. It's actually lower redshift, and it's an AGN. It's a quasar. And so you can see here with the spectroscopy, you have this broadened H-alpha line, and spectroscopically confirming that, nope, lambda CDM is intact, good. And it's not actually too massive too early. But this isn't where the story ends. After this, there's been a series of other papers. This is one that I'm highlighting is work led by Hollis Akins, a PhD student at UT Austin. And Hollis, on the Cosmos Web program, found in the very first few percent of that Cosmos Web data, a candidate redshift 8 red massive galaxy. And I thought in his paper, he did a really nice job summarizing the possible interpretations of this, this very red shape here with the flat UV slope. And so in these three possible scenarios, of which he favors, in this paper, they favor the dusty star-forming galaxy scenario. In this one, you have both an unobscured and obscured starburst. And so here you can see this is a super dusty, massive, but then there's also some patchy, basically patchy dust here. And so there's a composite that we're seeing, and then think back to what I showed you at the beginning. UV and IR, they're not always co-spatial, so you can have patchy dust. And we've known this for some time. The IR community in particular has been highlighting this with ALMA results. Other interpretations, as we already saw, unambiguous quasar, is that you have a quasar embedded, in this case, with a dusty starburst. Perhaps in this case, unlikely, because you wouldn't expect to have very little attenuation along the light of sight to be able to see that blue, the flat blue continuum here, or an unobscured starburst and a reddened quasar over here. But that reddened quasar luminosity would be really quite luminous relative to the underlying stellar populations. So more controversy, I don't know, maybe I shouldn't call it controversy, more information has come out. This is another recent paper led from the Eiger, a combination of the Eiger and Fresco surveys, where they have found a bunch more of these little red dots, what they call them, these candidate AGN, similar to what Dale Kozewski presented in his paper. This is just a subset of them. They all look little red dots, little red point sources. And so for 1/4 interpretation of a more recent paper, they're all recent actually, I don't know why I keep saying more recent. It's like last week or 2 weeks ago or 3 weeks ago. You can see this is one led by Evo, and this is now selecting more little red dots from the Uncover survey, which I'll talk more about shortly, in terms of quasar-quasar interpretation, where you have this red component is sorry, let's make sure. The reddened quasar is here, and then this flat component is scattered unobscured light. And so that also explains simultaneously why you might see the broadened H-alpha in addition. So seeing this composite. So this is work by Ivo Labe and Jenny Green, presenting yet another scenario. So, you know, there's lots of these candidates. Almost all of them are photometric candidates at this point. And so spectroscopy is really the critical piece that we need. And there is a program led by Erica Nelson that, at least for the remaining 5 candidates from that original paper, that will get spectroscopy and determine whether they're early massive galaxies, AGN. And you can see here, this is the probability distribution. The blue spikes are the narrow windows where it could be quasars. And the one quasar that Dale discovered indeed falls into this one narrow window, narrow redshift slice of possibility, whereas the other solution has a broader redshift range. And so, you know, time will tell. I don't have an answer yet for you in terms of what, but we have the capability to understand these in more detail. So what were my takeaways from the red universe? One, we should stay open to new discoveries in terms of looking at data. And maybe our original interpretation's not right, but no matter what, we learned something new with every step of this process and every new paper that came out and every new idea. So for me, it's been just a joy to see the different ideas coming out. The other lesson is that having high resolution and very sensitive, also longer wavelength observations, especially for these little red dots, were critical to enabling just the catalyst of the new discovery. And then the last point is that spectroscopy, I do photometry usually. I really don't do a lot of spectroscopy, so it feels ironic that I'm saying we need spectroscopy, but you know, every career can change as you go forward, right? You know, the spectroscopic follow-up was what has been critical in terms of understanding things. So I showed you the SMAX cluster. A lot of my time in the last year has been spent with Uncover. This is a beautiful image of the Abell 2744. It's a super remarkable cluster. It's sometimes called Pandora's cluster. This is where most of the Hubble imaging has been in the past, but it's actually a much bigger structure here of lots of subcluster. And so with Webb, we've opened up these two subcluster regions. There's always a jerk star in every field of view, so there's our jerk star. It really complicates things. And with this survey, and then this is also through the GLASS ERS program, there's been a wide range of science in this field, and this is deeper. So some of the deepest public data that we have in cycle 1 through the Uncover Treasury program as well as the ERS program. And so I'm not gonna, because I don't have a ton of time, I'm gonna go over this next part really quickly, but it's really just emphasizing what Claudia was talking about in the last talk in terms of the Lyman continuum. So I don't need to tell you about Lyman continuum, you've learned all about it. Thank you, Claudia. This is in that same cluster, but now there was questions of, okay, Claudia was arguing, oh, we need to do this at lower redshift. The most we can do is go out to redshift 4. Okay, let's take that example here. Let's use strong gravitational lensing, which amplifies the light and sort of like the best we can do. And what do we have right now with the existing Hubble imaging, which is in the cluster center? It's 8 orbit depth. According to our numbers, the most you would be sensitive to in terms of direct detection of Lyman continuum of a galaxy at redshift 3 to 4 is 2 or 3 if they had a really high escape fraction. So you're only sensitive to sort of like the tip of the iceberg here. And so on the right, I'm showing you just in terms of understanding what you should be able to see. I feel like this is too complicated to go into all the details, but the punchline is, I guess, twofold. One, we have wider area now with the Webb coverage, and we have spectroscopic redshifts. And so we can start to push down further with Hubble now in these fields. But at the end of the day, the punchline is that we really can't get below, with significant numbers, the 10% level in terms of direct detections. In terms of, it's just, Hubble is just not sensitive enough, it's not viable. Nobody would award us that much time. So, so here you can see that we can do direct detections, but really the idea is that most galaxies actually have much lower, the thought is anyways, that they have much lower escape fractions. And so the only way to push into where we think most galaxies live, and most of the galaxies that we think reionize the universe, and understanding this ionizing escape fraction is with something like HabWorlds. And so this is showing you, again, this is the cumulative number, but you can see here, what I want to emphasize is down to like this dot, is these are all below that 10% limit in terms of sensitivity. And the number of, hundreds of galaxies that we'll be able to do to directly detect Lyman continuum. Okay, wow, I'm gonna, okay. I studied quenched galaxies. I don't think I've talked about that yet. So I'm gonna spend my last 2 minutes and 30 seconds talking about quenched galaxies and why this relates to those little red dots that we saw earlier in this image. So this is work led by Jacqueline Antwi-Danso, who recently finished her PhD at Texas A&M. And what Jacqueline did is select candidate early quiescent massive dead, red and dead galaxies above a redshift of 3 from the Phoenix survey, and then went and used Keck to take spectroscopy and try to confirm spectroscopically, are they actually dead galaxies? Are they actually at higher redshift? And so this is shown here. You can see her Keck spectroscopy. This is the confirmed spectroscopic redshifts for her targets. What you'll notice here is that, so this is in prep, should be out any day now in the archive. One is confirmed as high as a redshift above, what is that, redshift 4.7. So very early in the universe. And then on the right here is showing a model of the star formation history. And so what I want to emphasize is for that particular galaxy is that most of its stars are forming in the epoch of reionization. And that's exactly the redshift range where we saw these candidate early massive galaxies. And so what does this mean? This would be consistent. The progenitor of these quiescent galaxies, the first quiescent galaxies, could be those early massive galaxies. And so this is interesting as a separate line of evidence that supports, okay, maybe there are some early massive galaxies. Maybe some galaxies formed earlier than we previously thought. This is another exciting thing where there's many. I was shocked to see how many approved programs there were for cycle 2, spectroscopic follow-up of redshift greater than 3 quiescent targets. This is listing this is their main science goal. So we have a lot of data that's coming and a lot that's going to be learned in this area. What surprised me is that there wasn't as much at lower redshifts, and so I'll return to that in a second. But there's also this paper that came out, another jaw dropper. This is work led by Adam Carnell. This is a quiescent galaxy at redshift 4.6. This is data. That's not a model, that's data. And again, if you look at the mass growth history, these are those early candidate massive galaxies. Again, it's consistent that these first quiescent galaxies would be early massive galaxies at higher redshift. Okay, 0 time. I talked very little about HabWorlds, bummer. So I really like to, I'm going into my questions period. What I'd like to learn is, I want to know more about quiescent galaxies. I want to be able to spatially resolve their stellar populations. I want the sensitivity, I want the resolution, and I want to understand this epoch here. This is their number density evolution. This is where most of the quiescent galaxies are forming. This is where they recently quenched. And so you want to look close to their epoch of formation before mergers and accretion dilute the signatures of quenching. And so this is the critical epoch we want to look at, and we want to be able to map their stellar populations, map alpha enhancements, which encode formation timescales. But it's hard to measure star formation rates. The age, dust, metallicity, degeneracy is no joke. And these galaxies are all tiny and faint. And so these are the key diagnostics we need. You can do it from the ground, but you have all these night skylines. You'll see it's less than 2 microns. So we're in the window of something where we need the sensitivity, even more so than Webb, more sensitivity to be able to actually map these galaxies. We need something like HabWorlds to make this leap. And doing things like in these galaxies, like revolutionary, like the Sparkler galaxy where you see these globular clusters, right? You need this sensitivity if we want to probe lower of the iceberg. So we need something like HabWorlds to be able to do this. What can we do now? Strong gravitational lensing always for the win. This is a remarkable redshift 2 galaxy. And you can see the source reconstruction. It will be getting also cycle 1 data later this year. And from this galaxy, if you were to use future near spec data, you can see that these are individual spaxels. So one spaxel is 0.1 arc seconds. And so you can actually, with these lens galaxies, you can actually map out their stellar populations and look at alpha enhancements and do these things. But this galaxy is 17th magnitude because it's strong lensed. Many, many, many magnitudes brighter than an unlensed galaxy of the same type. So we can't do this for all galaxies. There's a small few that we can with strong lensing. And so what do we need to do this? And there's also about 10 known dead lensed galaxies at this point. So I'd like to do more than 10 galaxies, right? We want to do a sample. So we need something like HabWorlds to be able to put this together to a picture. I'm gonna, oh, by the way, I managed to fit in dusty star forming and quasar. I'm agnostic to what the solution ends up being, people, in terms of those little red dots. It could be either, they're both cool. They both turn out to matter in terms of quenching a galaxy. Oh, that changed that. Instead of talking about this, I'm gonna take my last minus time to say something unrelated. So I talked to you a lot about discoveries that were made scientifically, but I think that there's been a lot of, I'm getting emotional. Sorry, I didn't see that coming. It's been a really intense year. And I had the opportunity to give a colloquium about my own academic journey. So it was a whole hour long. I tortured people telling them my story. And it was really cathartic to think about what are the lessons I've learned in my career, not just in the last year, but of being in academia. And so I thought it was important to point out, one, success is also an iceberg, just like we're only seeing the tip of galaxy's iceberg. So when you see other people's success, know that they've had Sorry. They've had a lot going. Sorry, I really don't know why okay. They've had a lot going underneath the surface. And so these are my takeaway lessons. One, this is not just for early career people, perhaps more importantly for everybody in the room, for senior people. Kindness is everything. How you treat people matters. So please treat people with kindness. Things almost never go the way you think they will, so you have to adjust your sails. Do what brings you joy. That doesn't just mean analyzing data through the weekend. That's fine sometimes, but we need work-life balance and we need other things. So find what brings you joy and do that and find the right balance. I was told early on in my career that you should fake it till you become it. And that really cannot ring more true. And then finally, related to this story of discovery, surround yourself with inspirational people and be open to surprise, because you just never know what you're going to find in data. And so I didn't talk a lot about HabWorlds because I skipped over that quickly, but just want to say that it's really new technology means those unknown unknowns are going to be coming. And so you have to be ready for them and be open. Thank you.
Thank you for a fantastic talk. Any questions? Well, great, because I have two. But I'll just one of them, the little red dots, you mentioned how similar they are to red and type 1 quasars. But we've seen from the work of Glickman and others that the most luminous red and type 1 quasars are in this wrecked galaxies, massive gas-rich mergers. And my question is, how many you said they're very compact. Are there any mergers? Is there any fuzz that could be interpreted?
So there is a recent paper that Josephine Bagman led of looking at the morphologies, at least of those 6 galaxies. The one confirmed quasar is the only unambiguous point source, meaning we don't see much else. That's it. The other ones have a little bit of fuzz. I don't think I'd ever say there's a merger there because, I don't know. I guess it would take much deeper observations. This is out of my realm in terms of separating out if you have a point source in the center and getting the underlying host morphology. But they are very compact, but not unresolved, which is interesting in terms of the interpretation. So this paper is on the archive.
Thank you. Any other question? Yes.
Hey, great talk. I was curious, you were showing, you can trace, the star formations. Can you also trace, the metallicity of stars at those averages?
So, yes, I skipped over it quite quickly. Metallicity has been something that has been really hard, and the way you want to do that is with absorption line signatures, and so you can get the chemical enrichment history. And decades of effort have gone into using ground-based telescopes, Keck, trying to do this, and it's ambitious, and you need, I think the Murska Creek, for example, has led a paper, and it was a 20-hour Keck spectrum, the deepest that we have, and the error bars are still huge for a global measurement, not even resolved. I showed this quite quickly here, but what I think is quite remarkable is this is encoding the chemical enrichment history and answering. And so that one black point is just one spaxel. So within the central kiloparsec of that lensed galaxy. So this is unique to strong lens things where you have that amplification. There's 54 spaxels where you could map out, right? And you could do it out to larger sizes, but just within that central core, which we think is quite critical in terms of understanding the formation of these galaxies, you could map out the chemical history. So yes, but you need higher resolution spectroscopy, and it really has been something until Webb that was out of our reach. But coming soon. That's actually is one of the things that hasn't come out in year 1, probably because it's really hard. And so people are there are groups that have data where you could do this. It's just not out yet.
Maybe while Ben is setting up.
Yeah, you showed a spectrum of looked like a post-starburst galaxy with a broad line on top. So maybe it's a post-starburst quasar.
Oh, the atoms, the redshift 4.6.
Yeah, the one that have spectrum like a star.
Yeah, and it's also sorry, I'll let you finish.
No,
your
it's
question.
very impressive.
Literally, I thought that was a model when I first saw it. But you also are cluing in, and it's very compact. If you look at the morphology, it's remarkably compact, that galaxy. I know less if they have more in terms of follow-up spectroscopy, but yes, that was one I think that was early, before JWST even launched. That was a candidate galaxy that was exciting to follow up. So, yes,
Yeah.
maybe
Yeah.
maybe there is, maybe that relates. I think it's discussed in his paper.
Yeah, so maybe a quasar forming after a starburst or something.
Yeah. Maybe we're finding the link, right? Yeah. Sorry, trying to get this out of my pocket.
That work? All right. Wow, I gotta follow that. Okay. So, bringing things in a little bit closer, we're going to look at nearby galaxies. I'd like to thank the organizers for inviting me here. I'm Ben Williams from the University of Washington. And I'm going to start with just a quick description of resolved stellar populations, and then talk about what HST has done, which is effectively just a revolution of what we could do with nearby galaxies in resolving their individual stars, and what we can maybe hope for HabWorlds would be able to do in the more distant future, and talk about what JWST is starting to do in that same regime. Talk about Roman, because that's also important. There's a lot going on with Roman in resolved stellar populations. And then finish up with some thoughts about how that fits in with the HabWorlds. So just to start with a quick description, we have a wide range of expertise in this room for sure, a wide range of presentations. And the reason that I think resolved stellar populations are important to the whole group are that they provide these details of the light production and the context simultaneously. You're seeing the stars that are actually producing the light that you're trying to interpret. And because of that, they're sensitive to stellar evolution models, they're sensitive to galaxy evolution, they're sensitive to cosmology, so they have a lot of applications. And they anchor our knowledge for interpreting unresolved, more distant systems. So when you're trying to figure out what's going on in those fuzzy blobs at redshift 7, it's nice to be able to tie them to stars that you've actually observed in the nearby universe whenever possible. You get lots and lots of these stars, so you can do lots of different statistical studies with different subsamples depending on your particular problem you're trying to attack. And so I like to think of this as stars as being a clock. They're effectively a fossil record, right? They generically time tag any events in the past, star-forming events, along with their associated masses and energies. And we basically, if you look at diagrams like this, I look at diagrams like this all the time. It's the color on the x-axis and the luminosity on the y-axis, and these are relative colors and luminosities of populations of stars. And stars at different ages, and they occupy different areas in this particular diagram. So by looking at the colors and brightnesses of stars, you can get a sense of what their formation, what their age distribution is, and reconstruct the evolution of the system that they live in. So you can take a diagram like this and transform it where every point in this diagram is an individual star, and you reconstruct the formation of all of those stars and get what we would call a star formation history or an age distribution for all the stars in that particular region. So you're constructing the formation of the galaxy, the evolution of the galaxy, as well as its metal enrichment and its chemical evolution. So people have been doing this for a long time, and it was easiest to start with the Magellanic Clouds because you can do that from the ground. You can resolve lots and lots of stars in the Magellanic Clouds. And this is an example of from back in 2009 where Harrison Zaritsky did this from the ground and got these beautiful color magnitude diagrams, lots of features in here that tell you the cumulative stellar mass as a function of age. So it's sort of backwards time here because we're starting here and we're accumulating stellar mass to the age of 0. But the nice thing is that people keep doing this, and the most recent measurements are still relatively consistent. You still see this formation history of the Large Magellanic Cloud. And so the technique has been well tested, been working for a very long time, and you're really doing it with the most detail that you possibly can. You're looking at each and every star that was formed, or as many of them as you can see. But it was limited from the ground to just galaxies near the Milky Way. Even M31, you couldn't really do a good job with this because if you look at M31 from the ground, if you zoom into some small area, you'll maybe be able to make out a few stars. Most of these are even blends. But then HST changed everything because you could take that, even in the M31 disk, you could resolve out stars to fairly faint luminosities. And so you could do something like, if you look at the local group back in 1998 and tried to look at the age distributions of stars in many of these galaxies, most of these were done from ground-based data, you'd get these very coarse estimates of what the age distributions of the stars in all of these in the local group galaxies were. And now with HST, you could go and do this in great detail. These are all cumulative age distributions for the stars in the local group. And you get these very detailed quantitative measurements of the uncertainties of all of the formation histories of all these galaxies in the local group that come from the resolved stars. And HST was so much better than the ground that we could actually go out to 4 megaparsecs and do this reliably. And so that expands the volume over which we can do this kind of work all the way to the M81 group. And so you can resolve individual stars and star-forming regions all the way out to M81 group and the Sculptor group. So once you start to reach out to these other groups of galaxies, you can start to get measurements of many different kinds of galaxies than what we would necessarily be able to get just in the local group, and you just expand the sample in interesting ways. So we were able to do that with HST, go and make color magnitude diagrams of the resolved stars in all of these different galaxies in the local volume outside the local group, and measure their formation histories. And one of the interesting results that came out of this way back when was that all these dwarf galaxies, because when you're limited by volume, you see almost all dwarf galaxies, have very complex star formation histories that are all quite different. And they're not just based on their morphologies, right? You can break these dwarfs up into different kinds of morphological types, and you still see a wide range of formation histories and evolutionary histories. But then the next thing we did, interestingly enough, we went back to M31 because M31 was really hard to do with Hubble, so it wasn't where we started because it's just so big on the sky. So M31, if this is the full moon, this is M31 to scale. The FAT project, which was a multi-cycle Hubble Treasury program, tiled over a large area of M31 in order to get a sense of what is going on with larger galaxies. The only other galaxy outside the Milky Way that we could really try and do this kind of detail, only other large spiral galaxy that we could do this for. So we covered this up. So this took over 400 pointings and years to do all the organizing and observing for. But in the end, we were able to get HST limited measurements of the stars in here. So if you look in the inner parts of M31, you see you get crowding limited photometry. No matter how long you expose in here, you're not going to see any more stars. In the outer disk, you actually can get much higher quality photometry, and that shows up when you transform these images into their constituent stars color magnitude diagrams. So here, like the blue here is the blue out here on the outside, where you get these beautiful features in the color magnitude diagram, tip of the red giant branch, red clump, AGB bump, main sequence. You get all these different features very nicely defined. But as you move into the middle, remember all of these, they all receive the same amount of exposure time, but down here in the middle of the galaxy where you have that severe crowding, you get much poorer photometry where you don't see the features nearly as well. We also were able to do this with, because of the parallel imaging capabilities of Hubble, we were able to get wavelengths all the way, or bands all the way from the near UV to the near IR. And so we were able to be sensitive to the types of stars for each and every star, which ones were hotter, which ones were sort of sun-like, which ones were the cooler stars. So we get much more sensitivity and extinction sensitivity because of this UV capability. And it would be nice to be able to go even farther to the UV because we would be able to access this bump in the extinction curve. This is 4 different model extinction curves over our band passes. And you can see the farther into the UV you go, the more sensitive you are to the shape of that extinction curve for being able to probe the properties of the dust and the extinction along the line of sight. So you can actually fit each and every star. This is sort of where things are going when you have lots of bands. So instead of just having 2 bands where you get a color and a magnitude and you're able to look at the color magnitude diagram, you look at all the bands simultaneously, look at the spectral energy distribution of every star, and you can then pull out parameters such as the mass of the star, the extinction to the star, the best fitting extinction law, the effective temperature, and do that for all your stars, all your 100 million or however many you get. And so that translates your color magnitude diagrams into actual HR diagrams where you have temperature on this axis and luminosity on this axis, and you can put actual evolutionary tracks on here to see what masses the stars are that you're probing and where they are in the evolutionary sequence. And then you can also play the same old game where you measure the history of star formation. So this is the cumulative stellar mass as a function of time by fitting 4 different kinds of models, but they all get a very similar answer here. And effectively, what you see in the FAT data, or what we found in the FAT data, was that most of M31 is actually quite old, and then it seemed to have had a pretty quiescent past. Whoop, went too far. And then it underwent some sort of star-forming event around 2 gig years ago, and all the models basically agree. And this is an interesting thing for the people simulating M31's halo structure, for example, and disk structure, because when you put this merger in at that time, it does help to recreate some of those features. So FAT did lots of things with the resolved stars, and I certainly can't get into all of them now, but I didn't even talk about star clusters, but thousands of star clusters. The youngest ones of those were then used to put precision constraints on the initial mass function of star formation. You can make maps of any kind of population you want, or maps of, in this case, the dust structure that you see from absorption. You can actually, because you can model all the stars, you can then make predictions of the emission those stars would have in other bands. So you can do things like predict the amount of Lyman continuum photons that should have been produced, and then compare that to what you actually see to try and determine escape fractions. You can measure star formation history and make maps of the stellar mass, and you can do detailed multi-wavelength work, like look for counterparts in the X-ray, or look for counterparts at other wavelengths that help you to do multi-wavelength studies of all types of stars. So, and we're currently working on getting the southern half of M31. We have about 90% of the data. In fact, there's some data being taken this week of this, so we should be able to map out the southern half. So then we will have some really gorgeous HST images of all of M31, hopefully coming out in the next year or two, where we combine the 2 data sets. And there's a lot more local group work, and local volume work with HST that keeps on going. Turns out there's lots of galaxies, and they have lots of stars in them. So it just keeps on going. So I just wanted to flash these up so that people can see there's just lots of work still going on. But I wanted to make sure I have time to talk about the future, because that's the point here. So what do we need to do this stuff? What we need is wavelength coverage. As you could see, we wanted to be able to tell the difference between hot stars and cool stars. We wanted to be able to tell the difference between one type of extinction and another type of extinction. We want to be able to get lots of depth so that we can see those important color magnitude diagram features to be able to tell how many stars there are of different ages. And we need resolution to be able to separate these different stars in crowded regions and get more stars on our measure more stars for any of these studies. So JWST is making progress on this. So I'm part of a early release science program for stellar populations for JWST, and one of the targets that we have is WLM, which is kind of which is a dwarf galaxy, star-forming dwarf galaxy that's on sort of the edge of the local group, about a megaparsec away. And it's great because it already has really high quality HST data. This is what we get from HST with 17 hours of exposure. And this is what we've got with NIRCam with 15 hours of exposure in exactly the same overlapping region. Twice as many stars. We go, here we see the bottom of this sort of subgiant branch, and we go well below that with JWST in less time. And so using that, we can get these really tight constraints of the formation of WLM. So here's the cumulative stellar mass formation for WLM. It's got most of the formation sort of took place, 6 to 2 gigayears ago. But the thing to look at here is how similar the answer between JWST and ACS was, or it is, which is very encouraging, right? It means that ACS basically gets the answer right, even though it doesn't have quite as high quality data as JWST does, but it means that we can go farther out with JWST and get just as high a quality measurement as we did with ACS closer to home. And JWST also does, most of that was just sensitivity gain, right? We just were able to see fainter stars because we got more collecting area. But we also do gain some some resolution with JWST in that, and here the first signs we've really been able to see of it in the resolved star regime is in the center of M33. There's a program by Eric Rosolowski that's looking at that has M33 imaging with NIRCam, and a postdoc at University of Washington is working on some of those data. Adam Smersina, and he's looking at just the very center to see how much better we do than HST. So this is our ACS data near the center of M33. And it's pretty good, but this is definitely crowding limited. And if we go to the JWST imaging, this is what the JWST imaging looks like for the same region, and we zoom in. It's better. It's not hugely better, but it is better, and it shows up when you look at the photometry. So here, if you look at our ACS data. We can see the red giant branch here. What did I do? Let's see if I can get that to come back. But we don't see the red clump, for example. And with JWST, this is again the matched regions, much less exposure time. But the difference here isn't so much the exposure time, because these data are actually a lot deeper than that. It's just that they can't resolve the stars below here. And so we definitely do have some improvement in resolution, but not a lot. In the IR, we do much better. So if you compare the IR from HST to JWST, it's significantly better, but that's where the resolution is actually much improved from HST. And it's because if you look at the JWST point spread function size, it's much smaller than the point spread function of HST because it's got a bigger mirror. And it also has pixels that are designed to sample that. So WST3-IR is undersampled, and it has a larger points per dimension in the IR, so it does much better. But if you look at HST in the optical, then your factor of 3 shorter in wavelength, factor of 3 smaller in mirror, and similar sampling, and so it's about the same. But JWST has the possibility of doing significantly better at its bluest bands, but then we're going to have to recover that because it's so undersampled. So this is the kind of thing I'm hoping that we won't have to do with HabWorlds so much. So this is showing sort of a similar effect. If you look at all the data from M31 and you say, how deep does it go? It's all the same exposure time. There's a wide range of depths, and those depths go all the way from 25th magnitude in say F160 to 20th magnitude in F160, and it's just because of crowding, because this on the x-axis here is the number of stars per square arc second, and it's all basically the same. There's always the same number of stars in the detector, and it's just a question of how far you get down before you hit that number of stars. And the same thing happens in ACS, but we go a little bit farther because ACS is better sampled and it's shorter wavelengths. So JWST is already going to push this to higher stellar densities, so we'll be able to see more stars in the infrared, and HabWorlds will hopefully be able to do this for bluer in the bluer bands. So that's what JWST is doing. I also wanted to talk about Roman because Roman's also coming up on the horizon and is going to be revolutionary in terms of field size for resolved stellar populations. And it's because if you look at, say, a galaxy like M101, where HST would give us kind of a pencil beam survey of just a small part of the disk, with Roman, we'll get not only effectively the whole main body of the galaxy, but also be able to probe these very low surface brightness halo regions of these nearby galaxies. And when you can separate when you can tell the difference between the stars in the background galaxies and these outer parts, you can probe very low surface brightnesses and start to look at the stellar halos of these particular galaxies, and not just finding structures such as these, where these are models from Bullock and Johnson from way back, but they effectively just nicely show that the stellar halos have different structures depending on the formation histories of different galaxies. And but in this case, not only we'll be able to find these structures with Roman, but we can also look at the colors and the populations of those structures, and make hopefully maps like these from pandas for M31, where you actually can probe, say, the metallicity of the different features in the M31 halo. And M31 has this amazingly structured halo with different with clear metallicity differences. And so Roman is going to make a great use of the local volume of galaxies, because while there are lots of the galaxies in the nearby universe, this is out to 10 megaparsecs, are just larger than the HST field of view by a lot. And they fit nicely onto Roman. So Roman's going to be covering all these galaxies and getting us, and these are the larger galaxies. These are the galaxies like M81 and M82. These are the galaxies that we really want to learn a lot about, but HST's had a harder time because it's got the smaller field of view. And just very quickly, our 414 Hubble pointings for M31 we'd cover with 2 Roman pointings. So things happen a lot faster all of a sudden. Okay, so let's. How am I doing? Oh, 2 minutes, perfect. Okay, great. So how does this fit into HabWorlds? So really, what we have with the idea with HabWorlds is the idea that we can reach to higher stellar densities than ever before, right? All of a sudden, we can get higher resolution telescope in space than we've ever had before. and it'll be at bluer wavelength, which helps even more. You make that numerator in lambda over d smaller, make the d bigger, great. And that expands our distance for which we can do these detailed studies. And the UV optical gives us lots of sensitivity for hot stars, which are the younger stars, the more massive stars. And it also potentially pushes down to that 0.2 micron extinction bump for getting characterizations of the dust along the line of sight to all these stars. And that's just to remind you, there's this extinction bump down here at about 0.2 microns that we could probe if we get down to 0.2 microns, which hopefully we would, and maybe even push farther if we can. And then I thought this sort of shows what we're up against. This is a great figure from the LUVOIR report that Tom Brown made that I really like. It's just schematic, but it is the actual locations of these galaxies, where this is the Milky Way, this is M31, and this is the distance out to which HST can reach, like the ancient main sequence turnoff. So see sort of all population ages, and if we want to be, and with JWST we'll be able to do that out a little bit farther, and with an 8 meter we can obviously do it farther. With a 15 meter we can do it farther. And as you go farther out, you gain access to all these different samples of galaxies. In particular, the way I like to think about it is that we have these great galaxy groups that are out at about 4 megaparsecs. We have the Sculptor group, and we have the M81 group. And so it's nice. It would be great to be able to reach those and have the similar data that we have for M31 today. So this is just the wish list, which I'll put up when I'm out of time. But really what we want is obviously the large aperture for resolution and sensitivity. And we want to push blue to at least 0.2 microns, which is the plan anyway, hopefully, to get temperature and extinction leverage. And we also want to have large fields of view to get those context and the details in these different structures simultaneously. So something like when you get to 10 to 12 meters and you get proper pixel sampling, then you can get these samples like M81 and Sen-A and the Sculptor group to be like the current quality of M31, which would be amazing. Right now we have essentially 2 big galaxies that we have at very high, that we have this kind of detail for, and we really open up the door if we can get to those groups at that sensitivity level, which would be sort of 5 times the Hubble diameter. Thanks.
Questions?
Is it on? Hey, hi. Mario Gennaro, Space Telescope. Hi, Ben. How you doing? Nice talk. Point well taken. JWST doesn't bias a lot in terms of turn-off ages. Stars are hotter than what JWST was designed for, right? So, and imaging in these wavelengths with larger mirror definitely needed. Can I ask you to comment on one capability that is sorely missed on HST, which is multi-object spectroscopy? What can we do in resolved stellar populations? I can think of globular clusters, multiple population done in spectroscopy, hot stars. So is there anything that a MOS would buy you besides just the imager on HWO?
Yeah, so for nearby galaxies, you're stuck with doing bright stars, but some of those are extremely interesting. And so one of the things that would be very helpful to get would be bright supergiant stars, which are always helpful to get, which are the ones that are sort of the most difficult to do stellar evolution modeling for. So getting spectroscopy for those with multi-object is one possibility. And there's always one of the great gains that we get that I didn't talk about is even for ground-based spectroscopic follow-up. So one of the things that FAT was fantastic for and that we're hoping to do with FAST and M31 is be able to do follow-up spectroscopy with Keck. Because even though most sources are blended from the ground, you can look with HST and figure out which ones aren't actually blended from the ground and then get their spectra. So, and that's good for doing kinematics. So doing kinematics is extremely helpful. And often can be used in conjunction with the population characteristics to tell you about what might have gone on in the past. In fact, one of the things that suggests that M31 has also undergone potentially this recent major merger is what's going on with the kinematics in the disk that's happened from the spectroscopic follow-up from FAT, for example. So yeah, spectroscopy is great. I don't do it, but I try to help people do it. Right.
Any other questions? Okay. So moving on to the next section. So Claire Murray will tell us about gas flows in galaxies.
Whoa, oops. All right, so is this working? Everyone can hear me? Awesome. So thank you all for being here. I'm really excited to tell you about what I think is a sort of out-of-the-box science case for habitable worlds, which is actually resolving gas flows in galaxies by their resolved stellar populations. And so for some extremely brief motivation, I like to show this image of the galaxy M74, or rather, its extremely dusty interstellar medium as seen through the eyes of JWST Miri, because when I first saw this image, I actually gasped because, you know, when you look at it, you can see that the interstellar medium of galaxies is organized into a fantastic array of morphological structure. You see bubbles, you see filaments, you see walls, you see clumps, basically any shape you can think of is there. And at least to me, this screams that the ISM is extremely dynamically complex. And the point that I'd like to hammer home here is that the detailed structures and properties of the gas and dust in galaxies actually give us an extremely precise record of the physics of galaxies. So physical processes operating on a wide range of spatial and temporal scales are actually like star formation, supernova, turbulence, magnetic fields, anything you like. You can trace its influence by looking at how it propagates into the interstellar medium. And so the reason why this is not a solved problem, and people in my field still have a job, is that it's really hard to do everything at once. So basically, to build a holistic picture, we need to know about the density, the temperature, the distance, the composition, the kinematics of the gas, and no single tracer does this at once. And so I'm actually, by trade, a radio astronomer, and so I'm used to looking at spectral lines and thinking about density and temperature. But here, I'm going to tell you about a totally different way of understanding this, and it's by looking at resolved stellar populations. And in particular, I'd like to emphasize, as Ben did in the previous talk, Ben set up a lot of what I'm going to say actually, that the color and brightness of stars has always informed our understanding of the interstellar medium. I think it's not surprising that we first learned about the ISM by looking at stars. We inferred extinction by dust clouds by noticing these dark blobs. And we also inferred that the Milky Way is full of interstellar medium by looking at the color and brightness of open clusters. I highly recommend this review by Katja Ferrier that came out in 2001 if you want to learn more about the history. But anyway, to say that in the past 100+ years we've come a long way is a dramatic understatement. Ben introduced the FAT survey to you in the last talk, and so I don't need to talk too much about it, but we've learned a ton about galaxies by their resolved stellar populations. In this talk, I'm going to focus in on slightly smaller scales. And so this is a region of the Large Magellanic Cloud, slightly bigger than a single HST footprint. And what I'd like to emphasize is we can learn a lot of information about individual objects by looking at the stars. So this includes the stars themselves, but also includes individual dusty gaseous structures along the line of sight. And so to do this, I'm going to emphasize the power of a particular tool. This tool is called the Beast. And the Beast doesn't actually have an official logo, but its author, Carl Gordon, likes to use this tiger. And so I'm going to show it here every time I talk about the Beast. And so the Beast stands for the Bayesian Extinction and Stellar Tool. And basically what it is it's a multi-wavelength SED fitter. So for every source in this field, you can extract its multi-wavelength photometry. And then the BEAST leverages stellar evolution and atmosphere models, plus a detailed treatment for dust extinction in order to infer a lot about the source, including the stellar age, mass, metallicity, and distance, as well as the dust extinction, the dust grain size distribution parameterized by RV, and also a measure of the extinction curve shape. And I'm highlighting those dust parameters not only because I love dust, but because I think this is what makes the BEAST unique relative to other similar tools. We're not treating the dust as a nuisance parameter. We're actually trying to understand its detailed properties in particular. And so I can't go on without emphasizing the fact that broad wavelength coverage is essential here. You can run the BEAST on a single band observation, but you're not going to get meaningful constraints on your source. And this is because, as Ben already showed, in order to distinguish between stars of different stellar types, and here I'm showing spectral energy distributions from A-type, G-type, M-type stars, you really need to cover the UV through the infrared. And these are normalized transmission curves from the FAT survey for reference. The same is true for dust, but of course, as Ben already pointed out, we're kind of missing a lot of information here at the far UV wavelengths, and this is something I'm going to get to later. Okay, so if you have your fabulous treasury survey of your favorite galaxy, like FAT of M31, what can you actually do with the BEAST? And so one example is work done by my fabulous graduate student, Christina Lindberg. She was able to produce by far the largest catalog of massive sources in M31 by looking at the BEAST fits to the millions of sources in this galaxy. And so every point here is a massive star in the galaxy. And not only can she characterize their intrinsic properties, but she can also characterize the ISM around these sources. And so they're all colored by AV, or the dust column density. And this is really exciting because we can not only learn about where massive stars form in galaxies, but we can also learn a lot about how they're influencing their surroundings. And I think this has a lot of important implications for topics we've already heard about this week, such as ionizing escape and how massive stars are interacting with the ISM around them. But to focus in on the topic of my talk, I'm going to talk about gas flows in galaxies. And so we're moving away from M31 and going over to the Large Magellanic Cloud here. This is a beautiful optical image of the LMC for those of you who don't spend your time looking at our nearest neighbor galaxy. I'm going to focus in on one region in particular, highlighted here, and this is the 30 Doradus region. So 30 Doradus is a very special region. It's the most luminous star-forming region in the local group, and so we have a beautiful archetype of starbursts in our own backyard, and we can look at its properties at extremely high resolution. And so I'm going to zoom in even farther into this small region in 30 Doradus. And so this is a 3-color image of the region from HST imaging, which I've colored in black and white on purpose, just to emphasize the fact that this is a very static picture of the dust in this region. We're not getting any information about how it's moving. And so in order to open up a new dimension, we need to add information from other tracers. And so here I'm overplotting a velocity map from high-resolution CO imaging of this same field. And so the parts of this map that are colored in blue are gas that is moving towards us, and the parts that are colored in red are gas that's moving away. And so we use emission and absorption line tracers of velocities to infer inflows and outflows all the time. But the problem is, without knowing where the gas is sitting along the line of sight, we can't tell if this region is exploding or collapsing. If the gas in blue is in front of the gas in red along the line of sight, that means it's moving, it's exploding. Whereas if the converse is true, the gas is collapsing along the line of sight. And so we need to probe the distance to these structures in order to break thought degeneracy. And so what should not be surprising is the BEAST is coming to the rescue to help us solve this problem. And so we can take every single source from a single HST field in this region. They're all colored in pink. We can isolate all the sources that are sitting behind these dense star-forming regions that are traced by CO. And we can use the fact that the BEAST measures the distances to the stars and their total extinction in order to build a global model of where the dust is sitting along the line of sight. And we can do this. I swept a lot under the rug, but the punchline is that the gas that is moving towards us is actually closer to us along the line of sight than the gas that's moving away. And this is super exciting. This is like one of the first times that we've been able to make a constraint like this in an external galaxy. And of course, The implication that gas is exploding along the line of sight is not surprising, given what we know about 30 Doradus. It's a massive star-forming region. We expect that it should have some sort of fabulous explosive activity. But what's really exciting is we don't have to stop here. I love the Magellanic Clouds, so I'm going to emphasize them here. This is the LMC and the small Magellanic Cloud on the right. And in cyan, I've highlighted where we had previous HST UV through infrared imaging of the two galaxies. And then in pink, I'm highlighting where we're getting new imaging from the ongoing Scylla survey. And so this is a hundreds of orbits imaging survey of the Magellanic Clouds that we're getting by riding along with Ulysses and imaging the galaxies in parallel. And so we'll be able to make this type of measurement across both galaxies, which is something we were just simply not able to do before because these two galaxies are so big on the sky that individual HST footprints could never possibly cover them in full. And so we're super excited to do this. The implication is we can go from individual regions, which are tens of parsecs on a side, to build up a picture, a global picture of how gas is flowing on kiloparsec scales in each one of these galaxies. And then even a bigger picture to understand how these two galaxies are interacting with each other and producing the, fantastic debris fields known as the Magellanic Bridge and Magellanic Stream. Right. Okay, so that's all well and good. This is stuff that we're doing now. But what does this mean for the Habitable Worlds Observatory? As a brief recap, BEAST science has really two main requirements. We need to be able to resolve individual sources so that we can accurately model their intrinsic properties. And we need wide wavelength coverage also so that we can do a good job of modeling their intrinsic properties. And as Ben already mentioned, currently we're limited to basically two galaxies and the Magellanic Clouds, but we can really only get a full resolved picture of these two galaxies, M31 and M33. And because these are our nearest galaxies and they've been so well studied, these are like household name galaxies that everybody knows and loves. Ben also showed this plot, but I also really like it because I think with Habitable Worlds, we have the opportunity to make many more of these systems into our nearest and dearest friends. And so, as Ben mentioned, we can not only probe more galaxies, but different types of galaxies, maybe elliptical galaxies. And for a picture of what that might look like, these are snapshot HST mosaics of galaxies at, I think, roughly around 10 megaparsecs away. These are from the Legis team. We can get nice, beautiful pictures of these galaxies, but we can't do the same type of BEAST science here because we simply can't resolve the individual stars. And so what I want to do is use a big enough telescope to allow all of these galaxies to become very familiar friends to all of us. And also, as Ben mentioned, we need wavelength coverage here, below about 200 nanometers, because this is where extinction gets interesting. We really want to be able to measure this parameter RV, which is, hand wavy, a measure of the dust grain size distribution. Understanding how massive stars process dust has been a topic of intense scrutiny. And if we can get resolved maps of RV across all of these galaxies, that would be fantastic. And so I'm really looking forward to that. And so with my last 21 seconds, I will conclude. We're doing a lot of work right now with HST to dissect our nearest galaxies. But Habitable Worlds has the power to push way beyond this. And so I hope we really think big in this development. So thank you.
Questions?
Nicolas Flagship, Space Telescope. So when you try to constrain the dust, why don't you use also emission? You seem to be very interested in the extinction, but do you also use the emission from the dust to try to constrain your model?
Absolutely. So the one of the powers of the BEAST is by modeling the total extinction from the stellar photometry, we get an independent tracer on the dust mass. And so one of the sort of caveats for using emission to trace dust is you have to make assumptions about how you convert between dust emission and dust mass, and those parameters are highly uncertain. And so one of our goals actually is to do exactly that, to calibrate the use of emission as a tracer of dust mass so that we can enable higher redshift studies to use emission more accurately, and also to understand what drives those emissivity concerns within the galaxies.
question so much as a comment that your lower left panel with the slice of the galaxy there is about the same size as the micro shutter array, where we could put, you know, hundreds of thousands of apertures to look at the gas emission in the ultraviolet, whether it's moving forward or back. Actually, this is a question. Don't you think that's awesome?
It's so awesome. I totally do. I think so. My work with looking at gas flows really relies on a synthesis of multi-wavelength tracers. We can't trace the kinematics of the gas with the stars, and so if we have multi-wavelength spectroscopy of the stars, also we can skip that step and or understand more about how the gas and the stars.
That was a yes or no question.
Oh yes, it's very awesome.
Thank you, Claire. Beautiful talk.
Okay. I think Mark wants to top your question.
Yeah, great talk. I had a question about camera design for this kind of work. So as you know, with Hubble, we have an IR channel and a UVis channel, which have different fields of view. So to get this broad wavelength, you have to sometimes wait 6 months to rotate. With LUVOIR and possibly for HabWorlds, we had designed a high definition camera, which the IR and the UVis channel had the same field of view. So it was split with a dichroic or mirrors or something so that you could simultaneously get the two. Does that make a difference? Do you have a preference in this kind of work?
I mean, yes, for convenience sake, it would be great. I think we're not limited by that. Because, as Ben and the FAT team really proved, we can do a lot with any kind of instrument configuration you can think of. And so I would rather have the other things than that. But yeah, I mean, it would make our lives easier for sure.
Let's thank Claire again. And the next talk is virtual by Luis Welsh, who will talk to us about a window to the first stars.
Can you see this okay?
Oops. Oh no, I think I ruined it. I'm sorry.
Oh no, sorry.
I ruined it. I quit Blue Jeans. Sorry.
Or maybe.
I'm so sorry.
That's okay. That's okay.
Thomas knows I'm useless already, so it's okay.
Oh, okay. Want to try again, Luis?
Yes.
Yes.
Can you see everything okay? Yeah. Or not yet? Okay. Can you hear me? Yes. Okay, perfect. So hi everyone, I'm Louise. I've really enjoyed being at the meeting virtually. I've learned a lot about habitable worlds, and I hope that through this talk you'll see how my science might tie into some of the goals of the observatory. But particularly I'm going to talk about near pristine DLAs and how they can be used to look at the properties of the first stars. And so the period in our universe's history that I'm really trying to probe is around 400 million years after the Big Bang, when these first stars are thought to have formed. And the key thing about this stellar population is that they're the only stars that are expected to form from gas that's made up entirely of hydrogen and helium. So they're expected to be, in principle, metal-free, which should mean that they are easy to identify. But there have been dedicated surveys that have spanned over 4 decades, and we're yet to find a metal-free star in the local universe. And that kind of ties in with what we see from simulations, which suggest that these stars may have been many times more massive than our own sun. And so one of the things that we can do, and we are doing, to try and observe this stellar population is go to higher redshift. And so with the James Webb Space Telescope, we'll now be able to explore higher redshifts than ever before, searching directly for these stars. And I think a lot of the science that can be done is kind of yet to be understood. So that's extremely exciting. But what we can do still in the local universe is look at the objects that we have detected. And while we haven't detected a metal-free star, we have detected an ever-increasing number of increasingly deficient in iron stars. And so these are known as the stellar relics. And as you get down to an iron to hydrogen abundance of around -3 and below, so this area that I've shaded in pink, you start to pick up some interesting chemical signatures in terms of the alpha elements, like carbon or possibly oxygen. And so from this study of stellar archaeology, we've learned that the chemical fingerprint of these population 3 stars could be encoded in some of the most metal-poor environments in the universe. And so if you imagine a massive population 3 star undergoing core collapse, it's going to enrich the surrounding gas with the first instances of heavy elements, and those heavy elements will eventually cool and collapse in that gas cloud to form the second generation of stars that we are detecting in the halo of the Milky Way. And I'm particularly interested in the intersection between these two objects, but for the most part I study gas, and in particular I study damped Lyman alpha systems, which are the ones that can be characterized by these very strong damped wings. And so if we're looking for the signature of the first stars in these gas reservoirs, we're looking for things that are in the extremely metal poor regime, which in principle is simple enough, but if you look at the metallicity distribution of these absorbers as a function of their column density, you can see that the region I'm interested in, which is around an x over h of -3, and if you look at the region where your DLA should be, when you look at a statistical sample, they're not making up an appreciable fraction of the population. So if you can see my mouse, it's over here. And maybe the question is, why are we targeting these highest column density absorbers if they're so difficult to find? But one of the key things about looking at DLAs is that they have a large enough column density of neutral hydrogen to be self-shielding from external radiation. And so that means when you observe the chemistry of these gas clouds, you don't have to apply ionization corrections, and so you can get the chemistry to a very high precision. And that's essentially what I enjoy working on the most. And in particular, I want to focus on the oxygen to iron abundance ratio of these systems. So in blue, I'm showing you the oxygen to iron abundance of metal poor DLAs, and in the background, I'm showing the same abundances, but for a sample of metal poor Milky Way halo stars. And I've shaded a region in pink, which is iron to hydrogen of -3 and below, where you can see this tentative increase in the oxygen to iron abundance. And we know from simulations of stellar evolution that this increase could be attributed to enrichment from a primordial population of stars. But to be confident in a trend like this, you would really want better quality data than what we have access to at the moment. And so over the past few years, what we've been doing is going after these systems in this regime and trying to get very high precision chemical abundances to kind of pin down the trend. And so we have data on all 4 systems in the extremely metal poor regime, but today I'm only going to present data on 2 of them. But the key thing to take away is that in the next year or so, we should have updated abundances for all of these. And so this system that I'm talking about first was circled by number 1. It was primarily placed to investigate this trend. And it's one of my favorite systems because kinematically it's very simple. So you can see that it's a single component structure. And we took more data with UVES for this target, which is around redshift 3. And the primary aim is to look at the iron 2 2382 line, because that's the strongest accessible iron line we have for these systems. And once we had this additional data, we were able to confirm it is indeed extremely metal poor and it is enhanced in oxygen to iron. So if you revisit this plot, just with one additional abundance determination at high precision, you can see that the trend that we see down in the extremely metal poor regime becomes a little bit more convincing compared to the oxygen to iron of the higher metallicity systems. And so with that in mind, we went after more data for this system I've highlighted in the red circle, which is in fact the most metal poor DLA that we know about based on the carbon and oxygen abundances. But the previous iron abundance determination was relatively weak. So again, we took the same observational approach and targeted the strongest accessible iron 2 line, which I'm showing now in the bottom right-hand panel. And you can see that with an additional 10 hours of Keck data, we were still unable to detect an appreciable amount of iron 2. And so we could improve the upper limit on this abundance ratio by around a factor of 1 dex. And if you plot this system on this plot of oxygen to iron, you can see it's following this trend of elevated oxygen to iron, which I think is becoming quite interesting, and we'll see what the rest of the data show. But it could be that we're seeing a divergence in the enrichment histories of these DLAs in one regime compared to the high metallicity systems, which I think is quite interesting. And just to highlight that there was some recent work that also looked at metal poor halo stars, and they took known stars from some of the most prominent surveys of these metal poor systems, but they reanalyzed the abundances using the updated information we have in terms of stellar atmospheres. So doing things like 3D stellar atmospheres and looking into the impact of lines that form out of local thermodynamic equilibrium. And so with these more sophisticated models, they were still seeing the same trend of an increased oxygen to iron abundance that we also see in the DLAs. And so I think that's relatively comforting that we're seeing the same elevation across these two different relic objects. And so beyond looking at empirical trends, we can also do things like compare with nucleosynthetic models. So here I'm showing the yields of population 3 supernovae as a function of their progenitor star mass and their explosion energy. And the key thing to take away is that if you have a system that's been enriched by one population 3 supernovae, you can use the chemistry to go back to work out the properties of the star that enriched it. But it could be that you have a system that's been enriched by multiple supernovae. And so to deal with that, I've developed a stochastic chemical enrichment model, which is aiming to understand the underlying IMF of the enriching population and also the number of stars that enrich the system. And the key thing, or the key diagnostic, is that the spread in the observed abundances you expect to see is going to change depending on the number of stars that enrich your system. And so once you have that, you can use the chemistry to work out the IMF. And I won't go into this in any detail, but the thing I wanted to highlight is that once you have an understanding of the enriching stars and their IMF, you can work out physical properties or infer physical properties like the stellar mass content and the total gas mass content, which can help you understand the place of these gas clouds in the wider field of galaxy evolution. And one of the things that I'm very keen to do is compare these near pristine DLAs at redshift 3 to the local ultra-faint dwarf galaxies that we see locally. And so one of the things that you can look at is whether the chemistry of these systems are consistent with one another, and does that hint towards a shared evolutionary relationship. And so that's what I've done here, just for the case of the carbon to hydrogen and iron to hydrogen abundance. And in fact, there's one star in Bootes 1 that shares a similar chemistry to the DLA that I was just talking about. And I think that in the future, that will be something interesting to explore. And I can see that I don't have very much time left, but I briefly wanted to also mention the carbon isotope ratio, which is a way that we can probe the existence of possible low mass population 3 stars, so population 3 stars that are around 1 solar mass. The carbon isotope ratio is a good way to do that, but it's very challenging to do because it's typically seen as an asymmetry in the absorption line profile. And so you need an ultra-stable spectrograph like espresso. And so I'll skip that. So one of the questions I have is that whether we'll be able to do these ultra-stable observations with something like the Habitable Worlds Observatory that we can do from the ground. And so looking into the future for this type of analysis, I am the first to acknowledge that we're currently limited by low number statistics, but as things develop, especially with the extremely large telescope, we're going to have access to far more sightlines, and we'll be able to find these DLAs towards fainter quasars, and we'll also be able to characterize a much larger number of chemical abundance ratios. And I think that in itself is very exciting. And so pushing to the Habitable Worlds Observatory, which in my mind is similar to UBES in space, I think there's a lot that can be done with this science. And maybe I'm thinking a little bit small, but the key thing that I've been looking at this past year is this iron 2 line, which for redshift 3 is often in a part of the spectrum that's impacted by telluric lines. And so doing it from the ground is quite challenging, and you have to time your observations well and be quite lucky in some respects in terms of where your lines form. And so if you can push this type of observations to space, then you're going to unlock a lot of potential in terms of doing high precision chemistry of near pristine gas. And I think that's quite exciting. So with that, I will leave you with my conclusions, which are that near pristine DLAs are really an ideal tracer of chemical evolution, and I think that this science is only going to grow in the next few decades.
Thank you. Any questions? Any questions online? So I guess on your wish list of things for the next observatories, what would you prioritize? The wavelength coverage, the sensitivity?
I think the key thing that I'm interested in is having the wavelength coverage in the near infrared from space, but also the sensitivity to have a high resolution spectrograph that's also that has a large enough collecting area to make appreciable gains in the number of systems. So I think one of the easiest ways to build statistics is, of course, to go towards the fainter targets. And I guess that I would prioritize above the other things.
Wonderful. Thank you. Any other questions? If not, let's thank Louise again.
Actually, Louise, we should probably talk later because I imagine there's an angle for HabWorlds to find the galaxies associated with these systems with the high.
Yes. That's also something I'm very keen on with the James Webb Space Telescope, but I didn't mention it because it's still quite early, but yes, indeed.
Thank you for coming. It's time to get our picture taken. We're going to go out on the front steps, and Gary's going to take our photo. We're about 10 minutes behind schedule, so I think we'll open the 1 p.m. activities. We'll start those about 10 minutes late. That would be the mentoring here in this room. And anything else that you've heard is scheduled for 1, just to give a little padding to get your lunch. So we'll do that, and then we'll try to get ourselves back on schedule by starting right at 2 o'clock.